We are going to talk a little about what is known as an analysis of variance. In our previous modules, as you have seen, you could take a continuously distributed outcome variable, and on a continuous outcome variable was regressed on either a continuous predictor variable or a combination of continuous predictor variables and categorical predictor variables. So now we're going to move the switch, switch things a little bit. In this particular case, instead of having a continuous predictor variable, we are now going to have a categorical predictor variable only. So think of this situation. Say, for example, you have got a drug, you're doing a drug test in which you have administered a medication that you want to find out the recovery time from an illness, say for example. And you've got two testing situations. That is, people who were given a drug versus a placebo. So, this time your predictor variable is actually has got two categories: people who received the drug, people who received the placebo. And your continuous variable, which is the outcome variable, is a continuous variable as to recovery times from the disease. What do you do in this particular case? Of course, your predictor variable is no more continuous. So in this particular situation, you will be using a technique known as analysis of variance. And R has got some excellent and very, very easy routines to help you work through this. And we will learn of those things in this module. So in this module, you're going to learn how to use analysis of variance in R, and how do we do this, and how do we run contrasts, how do we compare the different means that go across, what are some of the special cases, etc., etc. So remember that we are not going to do the details of the theory of ANOVA, but how to do ANOVA in R. Okay, so bring out your R Studio, load some data, and let's get working.
To reiterate the objectives is this, that we kind of introduce the concepts of one-way analysis of variance, one-way ANOVA. And we shall learn a few things. For example, how do we plot continuous variables and categorical explanatory variables, and we'll test multiple comparisons. Remember that in this particular module, the objective is not so much to discuss ANOVA and the theory of ANOVA and the statistical details of ANOVA, but the focus is rather on using or working with analysis of variance, and particularly one-way analysis of variance using R. So we may discuss a few theory bits here and there, but that is mostly in the context of how you can get R to work with this. So this is a distinction that you will need to keep in mind as you work with this. So as we said, ANOVA actually stands for analysis of variance, where the outcome is continuous and the predictors are all categorical. And in this particular setup, or in this particular tutorial, we are going to deal with one categorical explanatory variable and one non-categorical continuous outcome variable. So the way that works is this, that in the one-way analysis of variance, there is an overall partitioning of the variance in the outcomes to the factors and an error term. So if we wanted to set up a regression equation, you'd see that all of these different factors, there would be some partitioning of the variance. So within the within these levels, you'd have a variability, and then across these levels you have certain variation in the outcome variable. And if the variability across the different levels is much higher than within the levels, then you know that there is a significant difference, and that difference is something that you'd like to model here. Therefore, we are going to have categorical variables in R. Now, when we work with R and when we work with categorical variables in R, categorical variables in R are given a name which is known as a factor level variable. So, for example, if you are dealing with gender in R, and gender can have two levels here, male and female, then you can use or speak of gender in the context of R as a factor variable, and a factor will have two levels here, male and female. Something like a phenomenon which has got two answers, true or false, then true or false will be each level of the factor level variable of whatever that phenomenon that you're interested in. In our previous examples, when we were discussing simple linear regressions, we had been talking about parameters. And these parameters are called effects in the world of one-way ANOVA. And some effects are known as random effects, and other effects are known as fixed effects. We are not going to get into the nitty-gritty of what random effects and fixed effects mean here, but remember that R, and in this particular examples, R can measure both random and fixed effects. We will encounter random effects when we talk in terms of longitudinal studies and repeated measures. Here, remember that in one-way ANOVA in R measures fixed effects. So we continue with the concepts a little bit more. Remember that when if you have a variable which is a categorical variable with two levels, and if you had an outcome variable that was a continuous variable, then that continuous variable, if that were to be regressed on a factor, just two-factor level, a two-level factor, as an independent variable or an explanatory variable, one way to do that would be to conduct a t-test. So what ANOVA does is actually it extends that two-sample t-test, but this time it does for independent groups. And you're actually comparing more than two groups in this situation. So basically what happens is, based on that classification factor, you are subdividing the data into the groups, as many groups as the levels of the factors. And then using ANOVA, you are going to investigate whether the variability can be explained by the classification factor. So these factors are referred to as treatments, though in many circumstances you can use ANOVA as in the context of an observational study. So continuing with this, let us revisit our data set and see what we have for this. And as you know, we are going to revisit the data set that we've been using for some time now, which is the blood creatine phosphokinase data for athletes. And we had been studying this for some time now in this series of lectures. That is, whether weight and age would be two factors that can explain things. And we have, this time, we have decided to, we have removed observation 11 because it was influential. So we have also converted weight into a categorical variable. So weight is now less than 70, 71 to 74, and more than 74 kilograms. And so what we've done is, here I'm going to show you some other things that we may not have really covered so much in this series of lectures. So here's one thing that you can actually reclassify or reconfigure or recode a continuous variable into a categorical variable by using a very simple function which is known as cut. It works almost like the English language cut. So what you do is, and in this particular case what we have done is we have created a new variable which we named as weight rec. So our data set is blood CPK, and within the blood CPK data frame we decided to put a new variable whose name was weight rec. This name kind of signifies that we have decided to recode weight into a new categorical variable. So we said weight rec, and in that weight rec we decided to put recode the weight variable that was originally present in the blood CPK data frame. So blood CPK data frame is now cut. Obviously, when you cut something, you're going to insert some breaks in it. So you're going to discontinue. You're going to take a continuous variable and you're going to artificially discontinue that variable into a categorical variable. So you're going to put some breaks in it. That's exactly what it does. So you have to put the breaks. Where are we going to put the breaks? The first break is at 0 because it's quite intuitive that a weight 0 makes no sense. So that's the lowest one that we could, in theory, you could actually put the min weight in a.rm equals true, but we have just decided to put a break at 0, a theoretical 0. And then the next one we put a break at 70. This break could be based on a statistical univariate description of where the weights could go. So we just decided maybe 70 would be a ballpark that might be useful. Another breakpoint will be at 74, and our last breakpoint is at a maximum value of that weight. So we just max, it's a function, blood CPK $ weight. Now that gives you the breakpoints. So when we do this, R will kind of guess what this could be and put some levels on it. So we say the levels, we can specify it here. And you see how we have specified less than 70, 72, 74, and greater than or equal to 75. Going with the tradition of what is commonly taught in terms of what you should do when you analyze data, we decided to construct a box plot for this. So we have taken blood CPK, and in this particular case, out of the blood CPK, our variable of interest is creatine phosphokinase, and our observational variable, the other variable, of course, is our weight rec, which is the weight recoded. And the first thing is we put a box plot in it. And when you construct a box plot, which is probably the next thing, and you don't really have to, you could say it's a box plot, but you can also just use plot, and then on the left hand side using the using the formula interface, for instance, you can write the plot and then the outcome variable, the independent variables, the predictor variables, and the plot is going to give you a series of box plots. In this case, as it has done. So you have a visual inspection which suggests that the average blood creatine phosphokinase level is likely to be lower for those who are below 65 kilogram category, and there's almost like a monotonic increase in the weight in the blood CPK as the weight increases. So people with lowest body weight had lowest concentration of CPK, and correspondingly it just went up. And that is a visual inspection. So let us construct an ANOVA for this, so an analysis of variance for this. So let's write the model, the code, and then we do this. So the code goes like this, that we create a CPK model and store the linear model information into the CPK model object. So it's linear model, and CPK is the creatine phosphokinase, and then we put weight rec in it, and then we put the data, which is blood CPK. And we'll say we are going to summarize the CPK model. And when we do this, we just put summary of this. And then we print the summary of the CPK model. And this is what we get to see. Now, here is the thing. If you want to print the CPK model, and in this particular case, intercept does not really make sense, except that intercept kind of gives you a baseline from where you should start. It's more traditional that we do not put the interface, because what the interface does is interface artificially induces the lowest level. We'll take a look at this presently. So remember, in the second instance is where I have put the second model, but look here, in this case we have put a 0 before the weight rake because we removed the interface from the model, and we'll take a look at it and see what difference does it make. Study the way the coefficients have come out here. You can see that when we kept the intercept in the model, the intercept put an estimate of 200, put a standard error in it, and then gave you the p-value for this. And then the next level was weight recorded, the weight of the 65 to 74 kilogram category. And the estimate here was 138. So the first one was 280 and the next was 138. What that gave you was that relative to the to some sort of a theoretical 0, there was an increment of 138 over there. Doesn't make very intuitive sense, does it? And then the third category was greater than or equal to 75 kilogram category, and you can see that you have to increment by further 292. From a purely regression point of view, for instance, if there was a theoretical 0, that would make some sense. But that theoretical 0 was something like the intercept, and the intercept, when you take out the intercept, then you get a more traditional expectation as to what does it mean to have an ANOVA, in the sense that it is comparing the mean for each levels. You can separately print out the means, but in here, if you do not add the intercept term, then you see that ANOVA returns that the weight category of less than 65, that between 65 and 74, and above 75 years, so greater than or equal to 75 years, in each of these, the estimate kind of gives you that, what the weights are. I would not encourage you to take a look at the p-values of these individual categories, because they don't make much sense. What is really important is that overall, whether the model is statistically significant or not is what you want to test. Another thing that we do when we do analysis of variance, and particularly one-way analysis of variance, is to do what is known as multiple comparisons, which means that you compare between pairs of those variables. That is, you make a comparison between less than 65 and 65 and 74, or between 65 and 74 and greater than or equal to 75 kiloweights, or 65 less than 65 kilogram weights and that over 75 kilogram weights, and then you make a comparison as to how they stack up. But in doing that, you're actually introducing multiple comparisons. So you have to be a little bit conservative in how you can how valid comparisons you can make. And this is not trivial. This is very important, because if you make multiple comparisons, then you have to become conservative in the sense that any one pair of comparisons can be by chance can achieve a level of significance, but that does not necessarily mean that the entire sets of the entire variable with its various levels together is significant. It is a fine point. And there have been many different ways in which you can do this, but in R has implemented Tukey's honestly significant difference as the one that you can do. So what it does is, for multiple comparison, R uses Tukey's honestly significant difference. And in order to estimate that, you use a function known as Tukey HSD. And in the Tukey HSD, you actually use the AOV, or Analysis of Variance function, for a regression kind of equation, which is CPK, then the squiggly mark, which is kind of tilde, and then weight, recorded weight rec, and then you give the data, so the data is equal to blood CPK. So when we do this, it prints out the Tukey's honestly significant difference. The best way to understand this is to actually plot it out and take a look at that plot. So here is the plot. And if you examine this plot, you get to see that there is really, only between the second group there is a 0 point. And you can see that only for the comparison between the 75-year age group, out of the 3 possible comparisons, the second one, the mid one, that between greater than 75 and less than 75, the two extremes, is the only one that stands out as the true difference. So that is how you can see that there is a difference. However, you can see that, honestly speaking, there was none of these differences were really all that statistically significant. So although overall it's quite possible that it made some sense, but individual levels were not all that different as far as this is concerned. And it's difficult to see which one is, but you can see that there is a difference definitely between the lowest and the highest one. The second thing that is interesting for people who conduct analysis of variance is testing for the homogeneity of variance. And this is done with a test called Levin's test. And what we do here is this, that we take absolute values of the residuals. You treat them as response variables, or outcome variables, in a new regression or a new one-way ANOVA. And you have the same grouping variable. So in this particular case, we'll be taking the residuals of the regression equation that arose of the ANOVA initially in the first place as the as that, and the explanatory variable still remains the weight with its 3 categories. And then if the p-value is low, then the variance is non-constant. Right? So p-value very high will give you that there is homogeneity of the variance. The variance is homogeneous. Otherwise, the variance is non-homogeneous. And this is important because assumptions vary. So here is in our example case, you can see that here is where we see that that in none of this, and you can see overall, if you take a look at the p-value, you see that the homogeneity of variance test using the Levin's test, we see that there is a large p-value, and therefore we can't we do not have an evidence that a variance is non-constant. So you could say that there is a homogeneity, the variance is homogeneous. So those are some of the things that we generally study when we use an analysis of variance. You can get a nice graphical view, you can test the multiple comparisons, and when you put the analysis of variance in an R, it is a good idea, do not put the interaction or the intercept term. So these are some of the basic issues that we had learned how to do ANOVA in R. And the ANOVA table of means can be very easily constructed if you do not give an intercept using the no intercept model. And you can use multiple comparisons, use the Tukey's honestly significant difference test, and you can test for the homogeneity of variance using Levien's test. That's as simple as that. So this is all about using ANOVA, using R, and working with this. So thank you very much for your attention. In the next set of slides, we are going to take a look at what will happen in the context of regression, where you have got a continuous outcome variable and categorical explanatory variables, but instead of one variable or a pair, you're looking at two variables together. So there is a continuous outcome variable and two categorical variables, which is known as two-way ANOVA, and we'll take a look at that. So till then, happy working with your data. Thank you.
So this was ANOVA. In ANOVA, you learned that your outcome variable is a continuous variable, and your explanatory variable or your predictor variable is a categorical variable. But we dealt with only one variable situation. So just as we were doing with the simple linear regression, where we had one continuous and one predictor variable, here we had one continuous and one predictor variable. The continuous, one outcome variable which was continuous, and one predictor variable which was categorical. Kind of a special case of what you could do with a a two variables continuous case. Now we're going to learn a little bit more in details what happens when you've got two predictor variables, each of them is a categorical variable. This is known as two-way ANOVA, because now you're not doing it one-way ANOVA, one variable on which you can make the measurements. You got like cross classification of two different variables. And what do we do in those particular cases? Does R help us to do it? Of course it does. But how does R help us to do it? So that's the objective of two-way ANOVA.